My name is Chris Harris and I'm from Allery Chemistry, and this video is going to go through atomic structure in ions, and it's specifically designed for A-level bridging. So effectively what that means, this is perfect for you if you're doing GCSE chemistry, or you're going to do A-level chemistry next year, or you're going to do it soon. This is basically just an introduction, or trying to link some of the content that you would have done at GCSE and linking that in with A-level content. So the whole point of this is to basically make that link between the two, and just introduce you to some A-level content, but trying to bring that across from GCSE as well. So like I say, this is a bridging video. But what I've also done as well is I've created some multiple choice questions as well to go through the content that's on this video, and that'll be on the link in the comments box. So if you have a look at that, everything will be listed on there, and if you click on that, then you can have a go at the questions that's related to this. The questions also have answers with them, and it basically marks itself, so it's an electronic version. You click on it, and it will give you instant answers as well. So feel free to have a go at that to see if you've learned anything from the video. But as this is a link to A-level, my YouTube channel, Allery Chemistry, has loads of A-level videos, and it's all broken down into the main exam boards. That's AQA, OCR Salters, OCR, and EdXL. So everything is on there. So even if you're not doing the exam boards, then obviously it's still going to be relevant, because chemistry is chemistry. But it does have information that's specific to them exam boards. So there is loads of information on there. So please feel free to have a look. Okay, so the first thing we're going to look at is the atom. So the atom is basically the building block that makes up everything in chemistry. In the middle of the atom, we have a nucleus, and the nucleus is made up of protons and neutrons. So these are the subatomic particles that make up the middle of the nucleus. And what orbits the middle is the electrons, and the electrons have a negative charge, as you'll see in this table. So they have a negative charge, and it has a relative mass of 1 over 2,000. So that's just a mass that's used to basically measure relative to protons and neutrons, which both have a mass of 1. Your exam board at A-level, they sometimes use very specific figures. So you might say 1 over 2,000. You might see 1 over 1,860, for example. So you might see different types, but depending on the exam board that you're going to do at A-level will depend on what that is. So it is worth checking that. The protons have a relative charge of +1, so they're positive proton. Neutrons have a 0 charge, they're neutral, so it's neutral. And electrons have a negative charge, so that's a -1 charge. Now, you would have seen in the periodic table, you have a setup like this. You have your element in the middle, so in this case it's lithium, because Li. And the top number tells us the mass number, so that's the bigger number. Sometimes it's the other way around, but the bigger number is the mass number, basically. That tells us the number of protons and neutrons in the element. The bottom one shows us the atomic proton number, or it's also known as proton number, the atomic number. This just tells us the number of protons in the atom. And if we subtract them two numbers away from each other, we get the number of neutrons. So we can. The periodic table is vital for doing anything in chemistry. You're not going to get rid of that easily. But this has loads of information, and we can use that, and you'll see that later on as well. Remember that all atoms are neutral. They don't actually have a charge, because they've got the number of electrons and protons is the same. So if we have, in this case, we have 3 protons in lithium, so we'll have 3 electrons as well. Clearly this is different when we come to ions, which we'll look at now. Okay, so let's look at ions, like I say. So ions, the main difference between an ion and an atom is it has a different number of electrons. So they either gain electrons or lose electrons. So for example, the first type of ion is a negative ion. So oxygen is a classic example of a negative ion. There's other ones as well, such as nitrogen, which is in group 5, and then we've got the halogens in group 7. So they all form negative charges. So for example, oxygen gains 2 electrons to form O2-. It has 6 electrons in its outer shell, so to get a full shell, which is more stable for an atom to have a full shell of electrons, it's easier for it to gain 2 to get 8, which is the full shell, rather than lose its 6 that it's already got to get an empty shell, or a full or an empty shell is stable. So it gains 2 electrons. So in this case, oxygen forms 2-. Now, because it readily accepts 2 electrons to form O2-, then the number of electrons is going to be different to the number of protons. So you can see here the number of protons is 8. So we've got 8 protons there. And we've got 8 electrons. So we did have 8 electrons, but we've gained 2, so now that's 10. So you can see here we've got 10 electrons and 8 protons. We've still got 8 neutrons. That hasn't changed. They have a total charge of 0. So protons is plus 8 because we've got 8 of them, minus 10 electrons because we've got 10 electrons and they've all got a negative charge each. So the total charge is minus 2 for all of them. Okay, so positive ions, these are the opposites. So these are normally group 1s and group 2s, transition metals as well in the middle. They're a little bit funny, so don't worry too much about them. And then we've also got aluminium as well, so some of the group 3 elements. So in this case, the positive ions, they basically get rid of an electron, they lose an electron. So sodium in this example did have 11 electrons in total. So it had 1 electron in the outer shell because it's in group 1. You'll see that later as well. So it has 11 protons, that's plus 11. It has 10 electrons, which is minus 10 in total. So if we add all these up, neutrons, so these are 0, total charge is plus 1. Okay. Isotopes. So isotopes, basically these have the same number of protons but a different number of neutrons. So a classic example is carbon here. So you can see here, these are all elements of carbon. Remember the bottom number is the proton number, the atomic number. So this tells us the number of protons. These are all carbons, so there's no difference in the element. But what is different is the mass number at the top. That changes. So what I've done here is I've put the number of protons, neutrons, electrons for each here. Now what you'll notice is it has the same number of protons for all of the elements, but it has a different number of neutrons. So you can see the one on the left, this one here has 6 neutrons, this one has 7 neutrons, and this one has 8 neutrons. But notice the charge doesn't change. Just because we're getting more neutrons doesn't mean the charge is changing, because a neutron is neutral, remember, and the number of protons and electrons remains the same. Okay, so you need to know some definitions. You'll come across these in A-level more commonly. So you got the relative atomic mass, which is the average mass of an atom of an element when measured on a scale which the mass of an atom of carbon-12 is exactly 12. Now that sounds an absolute mouthful. You need to know these definitions for A-level, so you wouldn't have come across these at GCSE. But basically, in plain English, what that means is that the relative mass of all the elements in the periodic table is measured against one element, and that is carbon-12. Because carbon, if you add up all the isotopes, it is the one that's closest to the value of 12. So everything else is measured relative to that. So that's all it means. So, for example, if we have hydrogen, for example, so hydrogen is a mass of 1, helium is a mass of 2. So both of them have helium is heavier than hydrogen, so therefore the relative to each other, helium is heavier. So it's all to do with relative. It's not an actual mass, because obviously you can have different amounts of each. The relative molecular mass, you might have seen this at GCSE, but the main difference with relative molecular mass is this is the mass of molecules rather than individual atoms. So basically you just add up all the atoms, the masses, relative atomic masses of the atoms to get the relative molecular mass. And relative isotopic mass is pretty much the same as relative atomic mass, except we're measuring isotopes instead. So it's basically just the relative masses of different substances. Okay, so looking at electron configuration, now you would have seen at GCSE that you have a basic structure where you have 2 electrons in the inner shell and then 8 electrons in the shells after that. At A-level, what we do is we break that down a little bit more, and actually we have 4 subshells instead. So we have an S subshell, which can hold 2 electrons. So that's the first one. It's a bit like the first shell in an atom. But in other words, some of these shells here do actually have S subshells as well. So it's an orbital, we'll call it an S orbital, which has 2 electrons. A P orbital a P subshell has 3 orbitals in it. So hear me out here. Basically, that has 6 electrons in total. A D electron or D orbital subshell, D subshell has 5 orbitals, and that means it can hold 10 electrons. And the final one is F, which holds 14. So, for example, now if we link this with GCSE, so GCSE you had shell numbers. You had shell 1, shell 2, shell 3. So the first one, as you can see here, is shell 1. That has a 1s orbital, so we start at the first one. That means it has 2 electrons, so that's fine. That's what we'd expect at GCSE. The first shell has 2 electrons. At A-level, this is effectively, we can split that into a subshell, and that's 1s. Okay. The second shell, now at GCSE, you have 8 electrons in that second shell. At A level, that shell is actually split into 2 subshells. So that's 2s, and a 2p. So effectively, we know that an s electron has 2 electrons, and a p orbital, p subshell, sorry, has 3 orbitals in there, and each orbital can hold 2 electrons. So that means we've got 8. So that's how we split it up, and you can see the colours are colour-coded there. And shell 3 has a 3s, a 3p, and a 3d. So we have 2, and then 6 here, and then 10 here. So actually, in this shell, we can have up to 18 electrons. So this is why we use subshells, because the shell theory that you would have come across at GCSE, it's not wrong, it just doesn't go into full detail. And in this case, we actually can have more than 8 electrons in a shell. And that might seem a bit strange, but you will get used to it when you see this, because this is quite common at A level. Okay, so let's look at the configuration of some atoms. So if we look at the notation, so instead of writing a GCSE would have put 2883, and that would have been the electron configuration using shells. What we do is we strip that back and we use a different system, and you can see it here, which is the 1s2 bit here. So basically the 1 bit tells you the shell number, so that's the bit you would be familiar with, so that tells you, right, that's in shell 1. The next one tells you the subshell, so this is in an S subshell in this example. And 2 tells you the number of electrons, in that subshell as well. So in this case, we're in shell 1, subshell S, and it has 2 electrons in this case. Okay, so the electron configuration, let's have a look at this for iron. Now what we've done is we've split these subshells up into different areas. So remember, this is shell 1, that's shell 2, that's shell 3, and that's shell 4. Now they do get a little bit confused here, but you'll see these more at A level. You may not have seen these at GCSE, but you will see this a lot more at A level. So for iron, now we need to find iron in the periodic table. We know that iron has 26 electrons, because it's the number of protons equals the number of electrons. So it's 26 electrons. So what we're going to do is we're going to work our way through all of the subshells to see the configuration of it. So the first one is 1s2, so it has 2 electrons in the inner shell. And then the next shells, which is shell 2 is split into 2 subshells. So we've got 2s2 and 2p6. So remember, you can have 2 electrons in the s orbital and 6 in the p orbital. We then carry on. We've got 3 in shell 3. We've got 2 in the S subshell in shell 3. And shell 3 also has P subshells as well. So there they are there. And also, it has some in the S. So this is the next one. The reason why this is filling up here, this is where it gets a little bit confusing, is the 4S subshell is actually lower in energy than the 3D, this is why the basic shell model breaks down a little bit. This is why we use this model instead, because it allows us to explain energy levels of different shells. And then obviously there's then 6 electrons in the D subshell there. So basically, if we add all them numbers up, all the little numbers, that gives to 26. So that adds up to everything on there. But the notation in which we name them is always the same. We start at 1s2, 2s2, 2p6, 3s2, etc. And we keep going until we've used all of the electrons. And you can see here in the 3D subshell, we haven't filled them all up. So we always fill from the lowest energy. So we always start from 1s upwards. It's exactly the same at GCSE. When you are writing shell numbers, you start from the lowest shell first. In other words, shell number 1, which has 2 electrons, and then you move outwards. And we also fill the orbitals singly as well. So you can see here that we're not doubling up on any of these here. They sit into separate orbitals. This is because electrons have the same charge, and if we try and squash electrons into the same suborbital, they don't really like it. So it's not really it's another thing that happens in chemistry where we have electrons that are sitting into the same subshell, unless of course they have to. In other words, this one here has nowhere else to go but just pair up with another suborbital. It's a bit like people on a bus. So you'll find, I know it might sound strange, but you get people sitting on a bus. Some people don't want to sit next to another stranger. They'll find another seat to sit at instead. Unless, of course, all the seats are full, then you have to sit next to somebody. So electrons are a little bit like that. Okay, so the periodic table has got a lot of history. a lot of history, and it's evolved over numerous years. So this is very typical of science. Science never stands still. It's constantly evolving. We've got scientists coming up with new ideas, new explanations, trying to fit what we observe around us. So it really started in 1817, so it was an awful long time ago, where we had Dobereiner, and he came up with triads. Now Dobereiner basically grouped elements according to their characteristics. So he observed this, he watched this, and he observed it in terms of characteristics. And he realised elements like chlorine, bromine, and iodine had similar characteristics, and that bromine had a mass that fit halfway between chlorine and iodine. So therefore he thought, well, it's got to be somewhere between there. So he started ordering them in terms of their characteristics. And what he did is he actually grouped the elements into triads. So he grouped them into threes. And what he was trying to do was saying, right, well, I'm going to use these elements here and see there's a pattern between element A and element C, and B must be somewhere in between. So he grouped them. So he started. But it didn't explain everything in full. So Newlands came along in 1863, so it was quite a while later. And John Newlands started to take what Dobereiner had done, and he grouped the elements in terms of mass instead. So instead of looking at how they reacted, he said, well, actually, we can develop that a little bit more. And so what he noticed that every eighth element had similar properties. So this is where his octaves came from. He likened the pattern to octaves on a piano. So any musicians out there will know that you have. I'm not musical whatsoever. So, but you have apparently patterns of eight. You have eight blocks on a piano. So he did the same, and he was a musician. So he linked his music to his application of science. So it just shows you where some of these ideas come from. And basically, his theory broke down. His theory basically broke down when transition metals got involved, because it didn't fit that pattern of eight. They were an obscure bunch. So he improved on what Dobereiner come out with, but he wasn't quite there. So it wasn't until 1869 when Mendeleev actually created the periodic table. He got a hold of it, and he was a Russian scientist who came up with a new way of ordering it. So Dmitry Mendeleev took Newland's work and he adapted it, and he still ordered it by atomic mass. So he still honoured his way of thinking. But the big difference is that Mendeleev actually left gaps where Newlands didn't. So remember, Newlands couldn't find a place for some of the transition metals. That's the middle elements. So what this meant is that the elements were now grouped in terms of similar chemical properties. So he could do that now. And so Mendeleev was actually so confident he blended the properties of elements and ordered them in terms of mass, that actually what he could do is leave gaps. And that was the critical thing. He acknowledged that actually not all of the elements had been discovered at that point. And so he left gaps where they hadn't been discovered. But the key thing is that now scientists could take this, look for the gaps, and they knew roughly what they were looking for, because if they've seen the other elements in there, then they could work out what the properties were of the missing element, because it would fit a similar trend. So this is really powerful. So he was a bit of a smarty pants. So this is the modern periodic table. Obviously we've seen this before, but they're ordered actually in terms of proton number now instead of mass number, because it keeps them all in order. So it's a slight deviation away from that. But the groups are columns, and the electrons or the elements in the same group have the same number of electrons in the outer shell. So for example, in group 1, they all have 1 electron in the outer shell. And that group number relates to, like I say, the number of electrons. So, for example, if you had group 2, you'd have 2 electrons. Group 1, you have 1 electron, etc. Generally. And elements in the same group, they have similar properties. So this is building on Mendeleev's work. And he said group 1 elements all react with water with increase in vigour. So you've got, for example, lithium, which reacts with water, but nowhere near as much as rubidium and cesium, which are quite explosive in water. They're really vigorous reactions. So periods are row, hence where we get the word periodic table. And elements in the same period have the same number of electron shells. So just going back to that shell idea. So for example, this period here has the same number of electron shells all the way across. Different number of electrons in that shell, but the same shell number. So these elements are known as S block elements. So remember when we said about 1s2, 2s2, that bit before? That's where it fits in. Look, we have two. We have two spaces. So that's the S block, which is this bit here. This is the p block. Remember, again, on that subshell, we had 3 suborbitals, but 6 electrons could fit in. That coincides with this. 1, 2, 3, 4, 5, 6. So this is known as the p block. The purple block in the middle, that is known as the D block elements. So they kind of fit in, but they're not in part of a group. They're part of a, as like group 1 and group 2. They actually form a completely different setup altogether. And the final one, these are known as F block elements. You won't really come across these that much. They are a little bit out there. They're very heavy. These are like your uraniums, neptunium, americium, etc. So you've got loads of different elements there. Normally radioactive, them ones are not very stable. Okay, so calculating the relative atomic mass. So the relative atomic mass is the weighted average mass of the isotopes that make up an element, and we've seen that just before as well. So each isotope has a mass, and some are more abundant than others. Okay, and so to work out the relative atomic mass, what we do is we multiply the mass of each isotope by its relative percentage abundance, and we add it all up and divide it by 100. So the best way to explain this is by looking at an example. So here we've got an example of an element, but the element is made up of isotopes. So for example, just we've seen carbon actually exists as 3 main isotopes. That's what makes up carbon as an element. There's actually 3 different isotopes in there. This one has different isotopes. So we've got isotope of mass of 70, 72, 73, 74, and 75. And we've got the abundance. That basically means how much of that isotope is there in a sample. So basically, if we take a box of atoms and we had 100 atoms in there, approximately 20 and a half of them would have a mass of 70, 27.4 of them would be 72, 7.8 would be 73, etc. So that's basically what that means. So the relative atomic mass, like I say, is the abundance of an isotope times by the mass of that isotope plus the abundance of the next isotope, multiply that by the mass and divide it by the total abundance, which in this case is 100, because if we add up all them percentages, they add up to 100. So in this example, we're going to add up all the different parts at 70 times 20.5, 72 by 27.4, 73 by 7.8, etc. Divided by 100, and then if we add all that up, we get an answer of 72.6. And this is where we then look at the periodic table. We find an element with a mass of 72.6, or very close to, and in this case, this one's germanium. So germanium is actually made up of these 5 main isotopes, and that is just the average. So all them numbers that you see on the periodic table is actually the average of the isotopes that make them up. So that's what you see on the periodic table. So it's a little bit strange. Relative formula mass is a lot easier to work out. It's really straightforward. Basically, it's the mass of an element, of all the elements in a compound. We add them up, and that gets us the relative formula mass. Like I say, it's much more straightforward. So, for example, we'll look at 2 examples here. So the first example is working out the relative formula mass of aluminium chloride. So that's AlCl3. You might have seen this at GCSE as well. So the relative atomic mass of aluminium is 27. So we look in the periodic table for that. The relative atomic mass of chlorine is 35.5. So the relative molecular mass or formula mass, they basically have the same meaning. It's 27 plus 35.5, 35.5, and 35.5, because we have 3 chlorines, remember? So that's 133.5. And the next example is for calcium hydroxide. Now this one's a little bit trickier. I've thrown a little bit of a curveball in here. So we've got a calcium, which is 40. We've got an oxygen, 16, and a hydrogen, which is 1. But this bracket here tells us, and the number outside it tells us that we have 2 OHs in this compound here. So the MR of CaOH2 is 40. That's for calcium. We've got 2 16s because we've got 2 oxygens in there. Anything in that bracket is multiplied by the number outside it. And 1 and 1, which is 74. Okay, so fairly straightforward. Okay, so ionization. So ionization is and we've seen this just before about forming ions. Remember, it's gaining or losing electrons. Basically, the ionization in this case is the removal of electrons, and the definition is the removal of 1 mole of electrons by 1 mole of atoms in the gaseous state. So let's look at this example here. So we've got sodium, which is losing an electron. It's forming Na plus an electron. And the amount of energy it takes to remove an electron from sodium is 495.8 kilojoules per mole. So that's how much energy is required to remove that electron from sodium. So remember, it's got one electron in its outer shell for sodium. So always include state symbols. You'll see this a lot at A level. You might have seen little bits of it at GCSE, but this is a lot more common at A level. So always include state symbols. It's always in the gaseous state. And this ionization, because it requires energy, you're taking an electron from an atom, which requires energy. You can't just take it and have no, it doesn't take up any energy. It needs energy to do that. So the value is positive, so it's a positive energy value. So that's why we put a plus there. Okay. So basically, what affects ionization is something called shielding. Now, you might not have come across this at GCSE, so this would be quite a new thing at A level, but it is vitally important. You'll see it a lot at A level. Shielding is basically the protective effect of the positive nucleus in the middle to the outer electrons. So, for example, the reason why it takes energy to remove an electron from an atom is because there's an attraction between the positive nucleus in the middle of the atom and the outer electron, and there's a force. Now you have to pull that apart. It's a bit like having two bar magnets together, so that if they're quite far apart, there's not much of a force attracting them together, but as you push them magnets closer to each other, the force pulling them together becomes stronger. This is similar in an atom, except we've got a positive nucleus in the middle, which is trying to keep them electrons around its orbit, and so we need to put a little bit of energy in that. However, if that nucleus has numerous shells in between it, then we get what we call a shielding effect, and basically the more shells between the positive nucleus and the outer electron, the more shielding there is. And if there's more shielding, it means it's the attractive force between the positive nucleus and the electron is weaker, and so therefore it takes less energy to remove that electron from the outer shell. So that's quite a difficult concept to understand, but we call this shielding, as you can see on there. The other thing which affects ionization is the atomic size. So the bigger, again for the same reason, the bigger the atom, the further away that outer electron is from the positive nucleus. So that means it's much easier to remove an electron from a larger atom compared to a smaller one. So that's another reason, again similar reason to shielding. And the final one is nuclear charge. Now, I'll caveat this a little bit, but basically the bigger the atom as we go along a period, for example, the more protons we have in the nucleus, then the more protons means there's a bigger charge that's pulling these electrons in. But that's no good. This is the caveat bit. That's no good if you've got a lot of shielding between that positive nucleus and the outer electrons. So that isn't any good for that reason, but it is an important point to make, because the more protons you've got in a nucleus, the bigger the charge you've got, the bigger the attractive charge you've got. Okay, so let's look at first ionization. Let's look at the trends in groups using them theories that we've talked about, which is shielding, proton number, the number of protons, so the atomic charge, and the size of the atom. So if we look at group 2, now you might want to refer to a periodic table for this, but ionization energy decreases as we go down group 2. So let's go through them reasons again. So the atomic radius, as we go down a group, the atomic radius increases. So them outer electrons are further away from the nucleus, so therefore the energy required to remove it is going to be lower. Shielding also increases. We've got more shells because we're going down a group. So every time we go down a group, we introduce a new shell, and them shells protect the attractive forces between the outer electron and the nucleus as well. Now, this actually gives us strong evidence for the shell theory, which is the one that you've seen. Niels Bohr came up with that. Basically, he was the person who discovered that. Now, he came up with that, but it didn't actually explain data going across a period. So this is why, again, the subshell bit is so important, because although it explains shells, that's proof that there must be shells, because we wouldn't see this trend if there wasn't any shells. And shells still exist. It's just we can break that down into subshells. So if we go across a period, so we're going across period 3 now, this is along the periodic table, the ionization actually increases. So as we go across period 3, we have an increase in number of protons in the nucleus, so same number of shells, okay, as you'll see here. So the shielding is similar and the number of shells is the same, but the number of protons going across, obviously, if we go across a period, is increasing. So that's a higher attractive force. And actually the electrons are the same distance as we go across period 3. We're not adding shells, we're just adding electrons. So the attractive forces are getting stronger. So more energy is actually required to remove electrons from an outer shell as we go across a period. And this graph actually shows that. So let's look at ion formation, because we've looked at little bits to do with ionization there, and we've looked at the shielding and proton effect. So we look at the formation of them. So ions are effectively, or ionic compounds are held together by electrostatic attractions. And really what we want to try and look at here is the types of ions that are formed. There is another video that goes into bonding in a lot more detail, so I'm not going to go into this a lot here, but it's just showing you what an ion is and an introduction to the bonding process. So you can see here we've got an example of sodium and chlorine here. So sodium has a 1 electron in its outer shell and chlorine has 7. So this is only showing the outer shell electrons. Now, what these can do is these can bond together effectively. Sodium wants to have doesn't want a partially full subshell. So the easiest way for sodium to form a full or empty shell, is to give an electron away. So it's got 1 electron in its outer shell. For chlorine, it only needs 1 more. So actually, this is a perfect fit. So there we go. So there we are. So sodium actually gives the electron to the chlorine, and we have 2 ions that are formed. Sodium forms a +1 ion, chlorine forms a -1, and they actually attract together now because they're oppositely charged. So group 1s form +1 charges, group 2s form +2, group 3 form +3, the vast majority do. Group 5 form 3 minus ions. Again, not all, but some of them, for particular nitrogen and phosphorus at N and P there. Mainly because it gets a little bit confusing when you get down to bismuth and tin. It gets, because you've got other orbitals involved, but that's fine. Even at A level, you don't need to worry about that. Group 6 form 2 minus ions, so they prefer to receive 2 electrons, as we've seen before with oxygen. And group 7 form 1 minus ions because they accept an electron. So you might have seen this a little bit at GCSE. It's just showing the type of ions that form. The transition metal block in the middle there, they have varying oxidation, varying charges and oxidation states, which you'll look at later. But we'll go through that in a video as well. But as a whole, you need to know that what ions are formed and which in the group mainly dictates the ion that is formed. The ion that's formed on there. Okay, so you need to know as well some molecular ions. Now these are a little bit different. Obviously these are atomic ions here. So in other words, when I say atomic ion, these are elemental ions, should I say. So these, for example, lithium is +1, so it's Li+, Ni+, K+, Rb+, etc. We do have some molecular ions as well, and here's just some of them here that you just need to try and remember, really. You would have come across some of them. Hydroxide is OH-, nitrate is NO3-, ammonium is NH4+, sulfate is SO4 2-, carbonate CO3 2-. So you need to know some of them ions as well. Okay, so like I said, the transition metal ions don't really fit into a group, so it's not quite as simple for transition metals. What they have is they have variable oxidation states or numbers. So they don't actually have a fixed charge, such as all your group 1s have +1, all your group 2s are +2. These have varying different ones. And the main reason is they don't have ions with full electron shells, so that it's really difficult for them. So you might come across these. You don't need to remember these at all, but you might come across these. It's just really just to highlight that transition metals don't follow the same rules. So we've got some here. So you've got scandium, for example, which is on the left. But scandium is not a transition metal. Don't worry too much about that. So it only has 1. But you can see vanadium there, which is V, has loads of different oxidation states here, or different charges. Chromium has different types. Manganese has different types. Iron has 2 there. Cobalt, nickel, copper, titanium. So you can see we don't have, quite often we have varying charges. So don't worry too much about that. You will come across them at A level, but don't worry too much about that. Okay, so let's look at reduction and oxidation. You would have seen some of this at GCSE. What we're going to do is just drag this a little bit into A level and just adapt what you've got already. So electrons are transferred when reduction and oxidation occurs, and we use the acronym oil rig, and you would have seen that at GCSE. I'll be surprised if you haven't. So oxidation is the loss of electrons, reduction is the gain of electrons, so oil rig. So let's look at what this means in practical terms. So if we've got calcium, when calcium's completely burnt, so it's combustion reaction in oxygen, this involves reduction and oxidation, and we call this a redox reaction. So if we split this, we look at the bit that's been oxidized. So in this case, it's calcium, because calcium is losing electrons, and you can see here, calcium is forming Ca2+ to form 2 electrons. So that is losing electrons. So electrons are being produced. So, oops, we'll go the right way. And if we look at the oxygen side of it, that is being reduced. So the oxygen here, half O2, is receiving 2 electrons to form O2-, and it's the Ca2+ and O2- that join together to form calcium oxide. So that's been reduced. So you can see, because we've got oxidation and reduction happening, we've just split this into the 2 different parts. But if we combine these 2 equations, we get that. So we've got a redox reaction. You will come across this at A level. You might not have done it at GCSE, but we have chemicals which do this for us. So for example, we have agents. So a reducing agent lose electrons and are oxidized themselves. So in this example, calcium is the reducing agent here because it is losing electrons. It's been oxidized, but the agent this is what we call a reducing agent. Reducing agents are oxidized. Oxidizing agents, these gain electrons and are reduced themselves. So in this case, this is a reduction reaction. This one here has been reduced, but oxygen is the oxidizing agent. So there's a very close difference. Now, don't worry too much about this at the moment, but you will come across this at A level. So this is why this bridging video is basically designed to introduce elements of A level as well, so you get a little bit of a head start. Okay, oxidation numbers. So each element has been assigned an oxidation number or an oxidation state. Now the number depends on a set of rules. Now these rules, you may not have come across at GCSE. This is mainly encroaching into A level, but it's just to go through them so you get a little bit of a head start, like I say. So the rules are uncombined elements. Now you do need to know these. Mainly, this type of stuff is better through practice, through having the rules in front of you and practicing on loads of different elements. So you'll see that in a moment. But the rules are that any uncombined elements always have an oxidation state of 0. And oxidation numbers and states allow us to work out if something's been oxidized or reduced. This is why we need to know about it. So ions have an oxidation number that's the same as the charge of the ion itself. So for example, Cl- has an oxidation state of -1, Ca2+ has an oxidation state of +2. Group 1 elements are always +1. So potassium, for example, in potassium chloride, potassium is in group 1, so it always has a +1 charge. Group 2 always have a +2 charge, so for example, calcium and calcium oxide. And group 3, aluminium, not all group 3, aluminium always has a +3 charge, always. So wherever you see aluminium in a compound, you can assign it an oxidation number of +3. Hydrogen is always +1, except in hydrides where it's -1. You might not have come across hydrides at GCSE, but you will do in A level. So for example, HF, in this case it's +1, and this is a hydride example, is sodium hydride. So here it'll be -1 in this example. Chlorine is -1, except if it's in a compound with F and O, and it would have a positive value. So for example, potassium chloride, chlorine has a value of +3 in ClF3, so it depends on what it's actually bonded with, but most of the time it's -1 because it's got a -1 charge in group 7. The penultimate one is fluorine, is always -1, so there's no exceptions with this one. So KF, F in this case is -1. And the final one is oxygen, and that is always -2. It's always given an oxidation number of -2. And this has 2 exceptions, which makes it a little bit more complicated, but it's -1 in peroxides and +2 in a very specific compound, which is OF2. So, for example, in lithium oxide, Li2O, oxygen has an oxidation state in this example here of -2, but in peroxide, which is H2O2, oxygen has the value of -1. Right, so what we're going to do is we're going to use these rules, and we've dragged them across and condensed them to work out some oxidation states to show you where this example comes in. So we're going to work out the oxidation states of all the elements in red here. So NH3. So this adheres to rule 6. So rule 6 tells us that we've got hydrogen, which is +1, and in NH3 we've got 3 hydrogens. So that's +3 for the hydrogens. So the hydrogen is 1 times 3, which is +3. So because this compound is neutral, there's no overall charge, and nitrogen must be -3 in this case. H2S. So this adheres to rule 6. So rule 6, hydrogen is +1, except in hydrides, where it is -1. Well, in this case, it's not a hydride. This is +1. We've got 2 of them, so that's 2. The overall molecule is neutral, so that means sulfur must be -2. Do you see? So this is fairly straightforward once you get used to it. O2. So O2, this would be rule 1 because it's an element. It's an uncombined element. So O2 is the element itself. So it has an oxidation state of 0. So that's pretty straightforward. H2O2. Now you've seen this before because this is a peroxide. So this is rule 6 and 9. So we've got both here. So rule 6 is that hydrogen is +1. This is not a hydride, so this is +1. We've got 2 of them, so that's +2. So that means the oxygen, because this is neutral, we've got 2 oxygens there. Oxygen must be -1. But we know that from rule 9 as well, that except in peroxides, which this is, oxygen is -1. Okay. The next one is H2SO4, so sulfuric acid. So sulfur in this case we're looking for. So there's a few things we need to look at here. So rule 6 and 9 is that hydrogen we've got +1 for hydrogen. We've got 2 hydrogens there, as you can see. So we've got 2. So that means it's +2. The oxygen here, we've got 2 lots of 4 for the oxygen, which is here. This is rule 9. So we've got 2 lots of that. 4 lots of -2, so that's -8. So we have a +2, a -8, and the whole thing must add up to 0 because it's neutral, so therefore sulfur must be +6. And the final one is SO42-. Now this one's got an overall charge. So basically these numbers here must add up to -2. So we're going to look at sulfur here. So all these ones are neutral, basically, that's what we said before. But if we look here, we've got 2-, so we use rule 6 and 9. So we've got 4 lots of -2 because that's the oxygen. So that's going to give us -8. So the sulfur in this case must be +6. We know it's +6 because the overall charge must add up to -2 or 2-. So that's quite important. Okay. Okay, so transition metals have variable oxidation states, and these can actually be worked out. We just need to use a little bit more work to them because we've got other elements that we need to work it out from. But here's an example, which is iron oxide. So Fe2O3, we have 3 lots of -2, which is our 3 oxygens, so that's -6. So Fe must be +6 because the overall is neutral. But we've got 2 Fe's, so we need to divide that by 2, and that tells us the oxidation state of iron to be +3. Now you'll see this is where it gets a little bit different. Transition metals, to help us out a little bit, instead of writing iron oxide, we normally see Roman numerals between the iron and the oxide part. So the Roman numerals tells us the oxidation state of that element in that compound. So for example, this case it's iron 3 oxide because it's got an oxidation state of 3. So that's why we put a 3 there. And here's another example. This is why it's important, because this is also called iron oxide, which is FeO, except this one's got 1 oxygen, which is -2. So therefore iron in this case must be +2. So that means we call this iron 2 oxide. And so this is why there's a slight difference. It depends on what it's bonded with, because both of them are called iron oxide. They've just got 2 different charges or 2 different oxidation states. And this is why transition metals don't have fixed charges, as you can see. But you can work them out. And here's another example here, which is VO2+. So again, looking at the rules, oxygen's -2. The overall thing is a +2 charge. So that must mean that the oxidation state of vanadium is +4, because we add all that up, it adds to +2. So we call this vanadium 4 oxide because vanadium's got a +4 charge. And then if we look at this one, you can see these are very similar. VO2+, So again, we've got two oxygens here, so that's two lots of -2, because we've got two oxygens, that equals -4, and so vanadium must be +5. So we call this vanadium 5 oxide. But you see, this is why it's quite important, because you've got vanadium has various different oxidation numbers, and doesn't have a single charge. For example, it's not just all +1 or +2. So we need to identify them using Roman numerals in between. And that's it. So that's the first one. There's 6 videos in total, but this is the first one, looking at atomic structure and ions. Like I say, have a look on my YouTube channel, which is Allery Chemistry. It has loads of A-level videos on there as well. Also, just have a quick look at the questions relating to this, and the link in the comments box. All right, that's it. Bye bye.